Back in July and August of 2025, astronomers studying the interstellar object 3I/Atlas noticed something remarkable about its rotation. Observations indicated that it rotated with a period of 16 hours, with an extremely small uncertainty of just plus or minus 0.01 hours. This rotational period, derived from detailed photometric analysis and light curve measurements, provided an important baseline for understanding the object's behavior. For celestial bodies traveling through interstellar space, rotation periods can vary widely, but 16 hours is a moderate value, suggesting that the nucleus is relatively stable yet dynamic enough to exhibit complex surface activity. Accurately knowing this rotational period became critical, as it influenced how astronomers interpreted subsequent observations of jets and outflows emanating from the object. A rotation period dictates how ejected material should disperse over time, and any anomalies in the distribution of such material would hint at underlying phenomena that deviate from typical cometary behavior. In early November 2025, a series of preliminary images revealed a more perplexing phenomenon: a network of jets emerging from 3I/Atlas. These jets, captured and discussed in multiple observational reports, were surprising because the body's 16-hour rotation should have caused the material to smear or blur over time. When a comet rotates, any localized ejection of material is expected to trace arcs in space, producing a fan-like pattern rather than tightly focused streams. Yet the images taken by F. Niebling and M. Buechner on November 9, 2025, showed jets that were sharply collimated and extended to distances exceeding 1,000,000 kilometers. Given the expected thermal speed of sublimated volatiles from a natural comet, approximately 400 meters per second, it would take about a month for ejected material to traverse that distance. Over such a period, the nucleus would have completed dozens of rotations, which should have dispersed the material into a broad, smeared structure. Instead, the jets maintained their orientation with remarkable consistency, a fact that immediately raised significant questions about their origin. One possible explanation might involve a change in the rotation rate of 3I/Atlas since July, but this seems unlikely. In most cometary objects, asymmetrical outgassing acts to alter the rotation rather than stabilize it. In fact, uneven sublimation of gas often accelerates rotation or shifts its axis, making it difficult to imagine that natural outflows would slow the rotation sufficiently to preserve such narrowly focused jets. Unfortunately, no recent measurements of the rotation period have been published as of early November, though astronomers anticipate that updated data will provide insight into whether any rotational changes have occurred. Until then, alternative explanations are being considered to account for the striking observations. One natural hypothesis involves the specific angles at which sunlight illuminates pockets of ice on the nucleus. Cometary nuclei often feature highly irregular surfaces, including depressions, cliffs, and valleys that can shield ice from direct sunlight. When sunlight does reach these areas, sublimation occurs in localized bursts, producing narrow jets that repeat with the rotation period. For a nucleus rotating every 16 hours, this process would result in pulsating jets that appear as discrete puffs of gas. Given the thermal speed of 400 meters per second, each pulse would be separated by roughly 23,270 kilometers, meaning that a jet extending 1,000,000 kilometers would contain about 43 such distinct clumps. This mechanism naturally aligns the jets toward the sun, as the ice rapidly cools when not illuminated. However, this explanation cannot account for jets pointing away from the sun, which have been observed in images taken by M. Jaeger, G. Riemann, and E. Prosperi on November 8, 2025. These observations suggest that at least some of the jets are not solely the product of solar-driven sublimation, indicating that other processes might be at play. Another possibility is that the jets represent the evaporative trails of fragments ejected from the nucleus. If 3I/Atlas experienced partial disintegration or explosive activity near the sun, it could release smaller fragments that continue to outgas as they travel through space. This scenario would imply a more violent and complex history for the nucleus than initially assumed. Yet images taken by D. Jewett and J. Liu on November 11, 2025, show a single, apparently intact object. Reconciling the fragment hypothesis with observations of a coherent nucleus requires a scenario in which fragments are either extremely small, closely aligned, or produce only faint trails that are difficult to detect. Even so, the idea of fragment-driven jets introduces a significant complication, as it would suggest ongoing disruptive processes that could reshape our understanding of interstellar cometary behavior. A more speculative and controversial explanation is that the jets are artificially maintained by technological activity. In this scenario, 3I/Atlas might possess thrusters or other mechanisms capable of controlling the orientation of the outflows. Engineered propulsion could produce the collimated jets observed, maintaining their direction over vast distances regardless of the rotation of the nucleus. While such a hypothesis is extraordinary, the combination of persistent, tightly focused jets and unusual rotational alignment invites consideration of possibilities beyond natural processes. If proven, this would have profound implications, suggesting either extraterrestrial engineering or unknown mechanisms for orientation control in interstellar bodies. The observation of these jets adds a new anomaly to a growing list of unusual features associated with 3I/Atlas. So far, researchers have identified at least 12 significant anomalies, each challenging conventional cometary theory. The object's retrograde trajectory, closely aligned to within 5 degrees of the ecliptic plane of the solar system, is particularly striking. Statistical analysis indicates that such alignment has only a 0.2% chance of occurring randomly, raising questions about the forces that may have influenced its path prior to entering the solar system. This alignment is exceptional for interstellar objects, which typically approach the Sun at arbitrary angles, and suggests that 3I/Atlas may have undergone unique gravitational interactions or other processes during its journey. Additionally, the object displayed a sunward-directed jet or anti-tail during July and August, as well as in early November 2025. Unlike normal cometary tails, which are pushed away from the Sun by solar radiation and the solar wind, this anti-tail pointed directly toward the Sun. Observations confirm that this feature is genuine and not an optical illusion caused by perspective effects. The persistence of a sunward jet is highly unusual for natural comets, whose behavior is generally dominated by the outward flow of dust and gas. This anomaly further underscores the exceptional nature of 3I/Atlas and highlights the difficulty in explaining its activity using standard cometary models. Beyond these phenomena, the behavior of 3I/Atlas raises broader questions about the physics of interstellar objects. Its rotation, jet activity, and trajectory collectively challenge the existing frameworks used to model cometary behavior, especially for bodies originating outside the solar system. Each new observation provides critical data for understanding interstellar travel, the effects of solar radiation on small bodies, and potential mechanisms that allow jets to maintain orientation despite rotation. Future high-resolution imaging, spectroscopic analysis, and photometric monitoring will be essential to uncover the physical and possibly non-natural causes behind these phenomena. In conclusion, the interstellar object 3I/Atlas presents a complex puzzle for astronomers. Its jets remain sharply collimated over distances exceeding 1,000,000 kilometers, defying expectations based on its 16-hour rotation. Natural explanations, including solar-driven sublimation and fragment trails, offer partial but incomplete solutions. The speculative notion of technological activity, while extraordinary, provides a coherent explanation for the orientation and persistence of the jets. Coupled with its retrograde, ecliptic-aligned trajectory and sunward-directed jets, 3I/Atlas continues to challenge existing models of cometary and interstellar behavior. As further observations are conducted, astronomers hope to resolve these mysteries, uncovering the nature, origin, and extraordinary properties of one of the most enigmatic visitors to our solar system. Each new piece of data brings the scientific community closer to understanding whether 3I/Atlas is purely a natural object exhibiting unusual physics, a fragmenting cometary body, or perhaps something far more extraordinary, opening new frontiers in the study of interstellar objects and the limits of our knowledge about what travels through the cosmos.